Okay, so let us continue with the discussion here at hand, which is I am on the discussion of how to analyze a series RLC circuit. So sinabi nga natin that one method is we can solve this second order differential equation, but remember that this equation is in terms of charge. Okay, so if you are solving for if you are solving for current, you have to find whatever solution you would have for the current. Okay, whatever solution that you have for the current would be I mean for the charge would have to be differentiated in order for you to get the current. Okay, the current as a function of time. Okay, um now another method, okay, by which you can we can get around by this one is instead of actually solving this integral differential equation or this second order differential equation, we can use Laplace transform in order to solve this and this. Okay. Let's look at this at this equation muna. Okay. So I'll write it here. So this is the KVL equation. Okay. The Kirchhoff's voltage law equation um for your circuit. Okay. Series RLC circuit. Okay. If we take the Laplace transform of this, okay, this first term becomes taking the Laplace transform of this equation. Okay, taking its Laplace transform. Remember that I here is a function of t and as well as v here. Okay, so v is also a function of t. I just use the function names instead, v and I, in order for this not to be not to be really confusing. Okay, so when we take the Laplace transform of this one, we will have the following. We will have r times I, okay, which in this case I here, this I represents the Laplace transform of I of t, which is I of s. Okay, and then plus L. This is the derivative of I with respect to t. Okay, so the Laplace transform of of the first derivative of a function, okay, is basically s times I, minus I of 0. Okay, we'll explain what is I of 0 later on. Okay, plus this is the integral. So we recall that the Laplace of an integral is we divide s to the Laplace transform of the integrand. Okay, so this is 1 over c times I over s um, times I, again I here is I over s, I of s I mean. So I over s equals v. Okay, here v here now becomes v of s. Okay, so here is what this equation means. I of 0 here is the initial current. Okay, if it is possible that that your circuit has has an initial amount of current circling around the network. Okay, since again your inductor and your inductor and your inductor and your capacitor has the capability to store um, charges, okay, in different forms. Okay, so in that case it is possible that the charges stored in this in either the inductor or in in the capacitor can flow, thereby producing current. Okay, and that is without the presence of, for example, an input yet. Okay, so here's the complete equation. So we will have ri plus L times si, okay, minus L times I of 0, okay, plus 1 over C times I of s I over S equals V. Okay. Um, okay. There's actually another term here. Okay, another term here which actually tells us the initial charge. Okay. But that would actually come up. Okay, that would actually come out if we actually have this expressed in terms of this one. So if there is an initial charge, okay, not initial current, initial charge is Q of 0. Okay, that is your initial charge. Okay, if there is if the problem tells us that there is an initial charge, then there should be there should it would be more recommended more. It would be uh, more recommended that you express your equations in terms of this, because this initial charge would actually come out somewhere here. Okay, it actually would come out if you take the Laplace transform of this. Okay, it would appear over there. Okay, but if here's the case, if we assume that there's no initial conditions, okay, there are no initial conditions given in your circuit. Okay, that is, the circuit is at rest, or the circuit does not have any initial current or initial charge. I of 0 here becomes 0, and then our equation would simply become r of I. It would simply become r times I plus ls times I plus 1 over c times I over s equals V. Okay, and take note that this is the voltage for your resistance. Okay, remember KVL. The sum of the voltages around the voltage drops around a series circuit is equal to 0. Okay, so if we actually take back, if we actually rewrite this back in terms of the original KVL equation, which is this one. Okay, if we actually take it back here, we will notice that this is VR. Okay, this is VL, this is VL, and this is VC. This is the voltage across the resistor, this is the voltage across the inductor, and this is the voltage across the capacitor. Okay, now we take it one by one. Okay, we take it one by one. We will have this as VR. Okay, we have VR here. We have VR equals R times I. Okay, again, this I is I of S. It's a function of S. We are in the Laplace transform already. Okay, and if we actually take the ratio V over I, or the voltage across the component divided by the current flowing across the flowing to the component. Okay, this is equal to R. Okay, and this is what we define now as your impedance. Okay, this ratio in Laplace transform, this ratio in Laplace transform VR over I is what we call now the impedance. Okay, so that we say that the impedance across the impedance of a resistor is R. Okay, or the value of the resistance. Okay, while if we take that in terms of BN, okay, which is LSI, ratio BN over I is equal to LS, and LS is the impedance, okay, of the resistor of the inductor in Laplace transform. While VC, okay, we have here 1 over C times I over S. The ratio VC over I is the impedance of the capacitor, okay, which is 1 over CS. Okay, and this impedance, okay, although this impedance holds true only if your circuit is at rest, or the initial conditions, okay, the initial conditions of your circuit is are 0. The initial conditions are 0. Are 0, which would be a very good starting point in analyzing circuits, because most of we will consider circuits naman. Most of the circuits that we would like to consider, whether in theory or in or in practical in practice have zero initial conditions, or at least we could make it we could make the initial conditions to be zero. Okay, so, and this is what I'm talking about here. Okay, this is what I'm talking about here. If you may recall, these are the impedances in S domain. Okay, so my point is, my driving point here is that if you have a circuit, okay, if you have a circuit, you may want to and if the initial conditions are zero anyway, okay, you may want to just simply um you may want to simply express everything in the S domain. Okay, whether the impedances or the whether it's these are impedances or these are voltages or currents. Okay, we may want to express everything in S domain. Okay, so that is simply that's also the same as saying that we are taking the Laplace transform of your circuit. Okay, so that's not a practical that's not a practical operation, but it's just a thing, or it's just a concept that we would like to apply on our circuit. Okay, so let's try to apply it here on our example 3. Okay, so here what we would like to do here is we would like to solve for the current. Okay, we would like to solve for the current of this circuit. Okay, so let us have some space here. Okay, so as we can see, your circuit is a series combination. Okay, um, your circuit is a series combination of of capacitor and inductor. I mean a resistor. Okay, with an input voltage. Okay, it's just so happen that your input voltage is this one. Okay, but we'll deal with that later on. Okay, what I want to do here first is to express this current. Okay, I mean express the circuit in terms of its Laplace transform form. Its Laplace transform or in S domain form. Okay, we want to express this circuit in S domain form. Okay, so we do that by taking the Laplace transform of everything here. So the Laplace transform of B of t is B of S. Okay, so that's B of S. Okay, and then the impedance in S domain of the capacitor is 1 over Cs, as we have studied earlier. Okay, while R, okay, while R, the impedance of the impedance of the resistor in S domain is simply R. Okay, now what we're looking for is the current here. Now in time domain, that's I of t, but in S domain it is I of S, so we'll call that I of S. Okay, now from there we would like to we would like to have a what we call it, we would like to have a Kirchhoff's voltage law equation here. So we would like to have a KVL um equation here. Okay, now simply put, okay, this is a very very, and we also take note, we would like to be we would like to take note that the circuit is assumed to be quiescent. It means its initial conditions are zero. Okay, so this means that your initial conditions are zero. Okay, now um when the initial conditions are zero, this is the easiest way, or this is the easiest way to get your this is the easiest way to get your so the easiest way to get the KVL equation for a loop, okay, or within a loop, okay, is to add up the impedances, okay, then multiply the total impedance to the current flowing in the loop, okay, and then equate it to the impressed voltage or applied voltage into the circuit. Okay. and you would be able to use that idea, okay, when we actually add more loops in this circuit. Okay, but since we are dealing with a single loop circuit here, which we would limit it first to summing up the impedances, okay, which is 1 over C of S, 1 over CS, I mean, okay, plus R, okay, and then this is now the total impedance in your loop, okay, we call it the total impedance in the loop, okay, multiply this to the current, okay, which we will simply write as I, okay, again I here means I of S, okay, and then equate this to, or yeah, this should be equal to the voltage applied to the circuit, which is this one, or the voltage input. We will call this the voltage input, so this is V, okay, so that's the KVL equation for that one, okay, for this one, for this circuit, okay. Now let us try to express this as a single term, okay, so let's add this. We would have something like R CS plus 1 divided by CS multiplied to I equals V. Okay, and here we are trying to solve for I. Okay, we are trying to solve for I. Okay, so since we are trying to solve for I, we would like to um, we would like to isolate I here. Okay, which becomes CS over RCS plus 1, okay, plus 1 times V, okay, or let's divide this ratio with RC, so that we will make the leading coefficient of this S to be 1. Okay, we would like to make the coefficient of S here to be 1, so um, I'll set aside V first here. Okay, I would like to divide the numerator and the denominator here with with RC. Okay, so divide this by RC. Okay, and then divide this by RC. Okay, and then the V here is multiplied there. Then we will have um, 1 over R multiplied to S. Okay, it's 1 over R multiplied to S multiplied to S divided by S plus 1 over RC multiplied to V. Okay. Now let's talk about your V. Your V is square a square rectangular pulse. I mean, this is a rectangular pulse that is equal to V0 between A and V. Okay. So we can rewrite this in terms of your um I mean in terms of in terms of unit step functions, okay, as v of 0, okay, multiplied to u of t minus a minus u of t minus b, u of t minus b. Okay, so this is u of t minus b. Okay, now, so that is your v. Okay, so we write it here again. So v is v of 0 multiplied to u of t minus a minus u of t minus b. Okay, we would like to take the Laplace transform of that one. Let's make this lowercase, and let's write it instead as v of t. Okay, so that's v of t equals this one. Okay, so it's the Laplace transform. Okay, since VO here is a constant, remember that this is a flat or this is a horizontal line, so that's a constant. Okay, So we will simply take the Laplace transform of u of t minus a and u of t minus b. Okay. This is simply v o of e raised to negative as uh, over s. Okay. Minus v of 0 e e raised to negative ps over s. Okay. So this is what we will have to substitute here. Okay. So that I here becomes um, 1 over r multiplied to s plus 1 over sorry. Now, if we expand this, okay, if we multiply this term by term, we will have the following. So we will have v0 over r. Okay. S would cancel each other. This s in the numerator, this in the denominator would each cancel out. Okay. Then we will have e raised to negative as e raised to negative as over s plus 1 over rc. Okay. Minus v0 over r v0 over r multiplied to again s here in this numerator and the s here would cancel each other out. Okay. Then we will have e raised to negative vs negative es, okay, over s plus 1 over rc. Okay. Now, in this case, since we will be taking the inverse Laplace transform of a function, okay, having an s domain exponential, okay, having this uh, having this s exponential here and here. Again, as a rule, what we will do is we will set them aside. Okay, and what would remain is our f of s. Then we will take the Laplace transform of that. Okay, so in this case, if we set this aside, okay, if we set this s domain exponential here aside first, we will have v0 over r. Okay, v0 over r multiplied to 1 over s plus 1 over rc. Okay, in which case we take note that if we take the inverse Laplace of this, okay, if we take the inverse Laplace of this function, okay, we would have something like v of 0 over r multiplied to e raised to negative t over rc. Okay? So that would be its inverse Laplace transform. Okay? Take note that this term has the form 1 over s minus a, or s minus say s plus a. Okay? Where a here in this case is 1 over rc. So therefore its inverse, okay, its inverse Laplace transform is e raised to negative at, okay, and a here is to replace by 1 over r, so we will have this one. And of course vo over r are constant, so we will have to by linearity we will have to set them aside. So we will have this as our transform. Okay, but here what would happen is since actually that happens in both cases. Okay, that applies to both terms here, this term and this term. Okay, it's just that this is different. These two terms are different in the manner by which the first term, okay, the first term is multiplied by the exponential e raised to negative as, which should um, have the first term multiplied by u of t minus a, okay, and the second term by u of t minus b. But that's not all. Okay, remember that the inverse Laplace transform, okay, of e raised to negative as times f of s, okay, is equal to f of t minus a multiplied to u of t minus a. So which means we will have to multiply this, I mean we will have to replace this t with t minus a, okay, if the exponent is a, and then multiply it by u of t minus a, so that this first term becomes v0 over r times e raised to negative um, e raised to negative uh, t minus a t minus a over rc, okay, multiplied to u of t minus a, okay, minus v0 over r e raised to negative t minus b over rc multiplied to u of t minus b. Okay, so that is the inverse. Okay, and that's actually the current. Okay, now let us try to express this in another way. Okay, by taking note that you can actually rewrite. Okay, you can actually rewrite, for example, this term. Okay, you can actually rewrite that as v of 0 over r, v0 over r multiplied to e raised to a over rc, okay, which is essentially a constant, okay, and then multiplied to e raised to negative t over rc, and then multiplied to u of t minus a. That's for the first term. Okay, in the same manner we can rewrite this term in the same form, okay, with a replaced by b. Okay, so that is v0 over r multiplied to e raised to b over rc multiplied to e raised to negative t over rc multiplied to u of t multiplied to u of t uh, minus b, okay, in which you would be able to notice, okay, you would be able to notice outright that these factors vo over rz, this e raised to negative t over rc are common, in both terms. So we can factor them out. Okay, so we can factor them out. Okay, so uh, here is what will happen. Okay, we will have to factor them out. Okay, so we will have v0. By the way, this is already I of t, no? Kasi nasa t domain na tayo. Okay, we are in t domain already. So this is v0 over r e raised to negative t minus rc. Okay, multiplied now to e raised to a over rc u of t minus a minus e raised to b over rc. Okay, u of t minus b. Okay, now here's the thing. This is kind of different since you are subtracting two step functions here, but the scaling factor of each step function is different. Okay, therefore they will lead to different differences in different intervals. Okay, let me show you how that arises. So for example, we have here a unit step function. Okay, we have a unit step function that is defined as 1 for t greater than 1 and 0 for t less than 1. So this is essentially u of t minus 1. Okay, so this is u of t minus 1. Okay, now this is u of t minus 2. Okay, this would be u of t minus 2 because this is 1 for t greater than 2 and 0 for t less than 2. Okay, so that is u of t minus 2. Okay, now if we actually have if we multiply u1, okay, this one with 3, so its value it becomes constant at 3, while if we multiply this at 2, it becomes constant at 2. Now if we actually subtract them, and take note now that this is in this case now these two have different scaling factors. We have 3 here and then we have 2 here. This is what will happen. Okay, this is what will happen. Okay, at between 1 and 2. Okay, so between 1 and 2. Okay, between t equals 1 and t equals 2. Okay, the difference is actually 3 because at this point this function doesn't start yet. Okay, it is still 0 at this interval. Okay, so if you subtract this with this one and both of them have different intervals, okay, this is essentially 0 when t is 1 when t is between 1 and 2. Okay, so that is why you still have this one. Okay, but when the time or when t is now greater than 2, okay, they now become subtracted to each other. Okay, because this is essentially 3. Okay, at this interval this is 3. Okay, and then at this interval, okay, this is 2. So therefore this 3 minus 2, that becomes 1. Okay, so they only get subtracted after, okay, after t is greater than 2. Okay, so let's try to show them here. Okay, okay, so let me repeat now. Let me repeat. Here, at this interval, okay, at this interval, okay. By the way, the green, the red one, okay, the red line represents u of t minus 1. Okay. The blue one, okay, the blue line represents u of t minus 2, and the green one, okay, represents u of 3 u of t minus 1. Okay, so this represents 3 u of t minus 1 minus 2 u So 2u of t minus 2. Okay. So again, since they have different scaling factors, these two step functions have different scaling factors. The difference between them is not essentially zero. Okay. Unlike in windowing function where the scaling factor are both are equal. Okay. They have equal scaling factors. So therefore, at some point, the difference is bound to be zero. Okay. Here, the difference is not bound to be zero. Okay. Since they have different scaling factors. Okay. So take note that this is 3. Okay. From uh, from this just this term. Okay. Simply just this term. Okay. This is 3. From this is 3